Okay, so welcome to this industry talk for your Civil 473 course. My name is Saeed Hashemi from Jacobs Engineering, and today I will be talking about the application of optimization, specifically in water distribution systems. Hopefully, I will get another chance to talk about the application of optimization in sanitary wastewater collection systems in urban systems. But today we're going to use optimization to uh, find pump scheduling in optimal operation in water distribution systems. So before we go into it, I'd like to talk about a little about what I've done before and about myself, just so you know. So my background is in civil engineering from University of Tehran, and I also did a master's in civil engineering, more focused on water distribution systems. And I wrote a thesis on optimal pump scheduling in water distribution systems in order to minimize the energy used using variable speed pumps in pump scheduling systems. And I'm going to expand upon that specific topic with some further improvements throughout the years that we've accomplished with our research groups. After that, I did a PhD at Civil Engineering Department of Queen's University, again on energy assessment of water distribution systems, but this time instead of looking at pump scheduling and energy assessment on pump level, I looked at energy assessment at pipe level. So if you're interested in that, you can look up my thesis and see what it's all about, at least the introduction and the abstract of it. I am a professional engineer in Ontario and a project management professional with the global PMI. Recently, I've been working as an adjunct professor in Iran, and I have started my consulting work since 2008. So since 2008, it's been a combination of working in consulting, sometimes full-time, sometimes part-time, and at the same time doing my research, sometimes full-time, sometimes part-time. I started with Jacobs Engineering in Toronto back in 2017, mainly as a hydraulic modeling engineer and recently as a project manager. So I work on water, wastewater, and stormwater systems, optimization projects, master planning, calibration, and transient analysis. So in consulting, I do quite different stuff, but academically, I've mainly associated myself with energy assessment in water distribution systems. So you can check out my publications if you would like. There's a little highlight of what I've done within the last 10-12 years, different journal publications and conferences that I have attended, and I've given some talks about my research if you're interested to look at those. Now, I'd like to give you a little summary about where we are in the realm of civil engineering. So if civil engineering is at the top, one of the things we'll look at, one of the realms or topics would be water or water and wastewater. Under that, we have hydraulics, hydrology, and treatment. Today, we're mainly focused about hydraulics, modeling and simulation of hydraulics in water systems. And under hydraulics, we could look at rivers engineering, hydraulic structures, or the hydraulics and pipes and conduits like water distribution networks or sanitary collection networks. So we're going to look at conduits today, systems of conduits, and we're going to look at the application of optimization in this system of conduits. So as you might know, hydraulics is mainly about mechanical behavior of fluids as opposed to hydrology. That's about where the water is coming from, where it's going in the water process around the planet, or treatment that's mainly about biological processes or chemical processes when it comes to guaranteeing the quality of the water or wastewater. So all those mechanical behaviors would be based on how the fluid moves in these conduits, and they're all based on the good old Bernoulli equation. And our goal is to look at mainly pressure and flow rates in those elements in, for example, water distribution systems. Also, in my talks, I look at water and wastewater systems as an integrated thing or concept, just like this anatomical analogy. Even though we're today mainly focused on water distribution systems, I'd like to give you this sort of integrated way of looking at water and wastewater systems, especially in Southern Ontario, where we talk about lake-based systems. We get the water, fresh water, from the lake, treat it in the treatment plant, and then we pump it into the distribution system, and then through the sanitary collection system, we collect the sanitary loads or the sewage, and then bring it back somewhere close to the lake, not in the lake yet, but in the treatment plant, wastewater treatment plant this time, and then after treating it, we're going to release it into the lake. So the water is basically kind of circling in the form of water, wastewater, and every time before it's like, as it cycles, it is treated twice. So the fresh water is pumped into the system, just like the pump station that could basically act as the heart of the system in the water system, delivering water to the consumers, which would be tantamount to delivering the oxygenated blood into the different parts of the body, and the pipes are those arteries. And similarly, wastewater is collected through the veins that could be basically sewers, and it's going to be somehow treated in our body, and it's circling round and round and round. So now that we talked about the heart of the system, that's the pump station, basically, I'd like to talk to you about pump scheduling optimization. So this is a schematic of a real system that I worked on my master's thesis several years ago. This is on the top right, you can see this skeletonized schematic of this real system that is probably like half an hour east of Tehran, the capital city of Iran. And as a very simple example, I've picked one of the junctions, and you can see in the two plots bottom left, the one that's on the top is showing how the demand is changing throughout the day. That's the diurnal pattern. And how quite kind of opposite to that, the pressure is changing at the same time. They have an indirect or like opposite correlation, which is usually the case in the distribution system. So the demand throughout the day would change everywhere around the system because of the human activities that are sometimes a little bit more intense throughout the day and sometimes less intense. And with that in mind, we would want to adjust our pumping regime in the system to save energy, basically. This is the pumping regime based on our diurnal curve that I showed you. So in this system that we had four pumps in the pump station, if we want to explore different solutions, possible solutions for pumping, if we only think about turning on and turning off any of the pumps, and if we assume that there are four pumps, and we want to find the pumping status for 24 hours, then the possible solutions are 2 to the power of p to the power of 24, meaning that on and off, two pumping states to the power number of pumps, in this case 4 pumps as you can see on the right hand side, and throughout 24 hours. And you can see we have a lot of different possible solutions to comb through and find an optimal solution that is you know, adjusted to our demand pattern. Which pumps should be turned on, which pumps should be turned off, and that's why we should use optimization. Now, to get it a little bit more complicated, if we have more pumping states or statuses, such as variable speed driving, which is more than just the state of being on or off, which would be somewhere relative speeds of between 0 and 1, then this could get up to many solutions. If we assume that we could have 10 different speeds between 0 and 1, then it would be 10 to the power of p to the power of 24, p in this case 4 pumps, and that would be 10 to the power 96. Now, if we want to analyze all those solutions, then it is, and if we assume that each simulation is going to take only 2 seconds, which is very optimistic in a real system, then it is going to take probably 10, off the top of my head, 10 to the power of 88 years to just run this to find the optimal solution if we want to just run for all the possible solutions, which is not possible. So we basically use optimization, which is a kind of guided search through the whole search space to find the optimal solution without testing out all those possible solutions. Okay, so usually what we're trying to minimize is the horsepower of the pump station, usually, to save some energy throughout the day. So that's going to be gamma times Q times H, as I've shown in here, just to give you a little background about what pump scheduling optimization is all about, what we're trying to achieve, to minimize energy based on the pumping regime, and the fact that we have a lot of different solutions that we can't really go through, but we are going to use optimization to run probably 10 or 20,000 solutions and find the optimal solution, instead of running 7.9 to the power of 28 or 10 to the power of 96 different solutions, which would have been impossible. So as I kind of looked at the whole scenario of pump scheduling, it used to be a novel idea back in the time when I was working on my research or like master's thesis at the time. But right now, we have in InfoWater by Innovise or WaterGEMS by Bentley, we have these optimization tools in these software packages. But the problem is that in big systems, when you're using variable speed pumps, they don't quite work and they don't give you satisfactory results. And with that, I'm going to show you some of the case studies that we have recently worked on and published in the Journal of Water Resources Management. If you're interested, you can definitely look that up and see the details of what I'm about to share with you. So in that study, we looked at 2 different case studies. The one on the left is by Laroque et al., and the one on the right-hand side is a real system in Iran serving a population of 100,000 people with a quite significant daily demand. Okay, so we usually test out our ideas for a sample system that is like a benchmark system studied by a lot of different researchers. And we tried to test it out also on a real system that would be around in consulting work to show that it's working. And the results that we came up with. So before I go into the pump scheduling scenarios, we used MATLAB for that matter. We combined MATLAB to our hydraulic engine, which is EPANet, which is open source. You can program it, you can code it, and we use particle swarm optimization. Just so you know, you can use any other kind of optimization algorithm. I used back in the time ant colony optimization, and the two software packages that we use in consulting mainly these days, they use genetic algorithm. So the optimization algorithm really doesn't matter as long as you know what you're after and what your decision variable is. Your decision variable is the pumping status for any of the pumps throughout the day. So what are we looking at here? We're looking at different pumping scenarios. The pumping scenario number 1 that I have not shown in here assumes all the pumps in both pump stations are on. And here also I need to add this note that we're presenting the results for the sample case study, but the results are very, very similar for the real case study, but it would be a little bit hard to communicate through a few slides. If you'd like to know more about it, definitely look up the paper and you can see more details for the real case study. But the results are very similar and the conclusions exactly the same. So top row would show pump station number 1, in which we have 4 pumps. Bottom row shows pump station number 2 in that hypothetical sample system that has 6 pumps in it. Okay, so in the first mode or scenario of pumping that I'm not showing in here because it's not very exciting, but we're going to have it as a part of our comparisons, which is our baseline scenario. Leave all the pumps on, and I am totally aware that it's not a very practical scenario, but just for the sake of comparison, I'm mentioning it, and in terms of comparing the costs, the power consumed, how the leakage is improved, how the performance of the system is improved, we're going to compare all these 4 other pumping scenarios to that baseline scenario that assumes all of the pumps in both pump stations are on. So let's look at this second mode or second scenario of pumping, in which we are using the number of active pumps. So what we did, as opposed to what's done in those software packages, is that in the software packages like WaterGEMS and InfoWater, what happens is you set the different pumping statuses, and then the software will find the optimal solution for those pumping statuses. And the problem arises when you have too many pumps and you have too many different pump statuses, like using variable speed drives. But here, the trick that we used in order to improve the solutions provided by WaterGEMS or InfoWater is that, first of all, we're optimizing the number of active pumps. So we run the optimization, we find, and we calculate how many active pumps we need throughout the day, and then after we realize that, we're going to optimize the pumping status for those. So in this scenario, we're still using fixed speed pumps, but we're using number of active pumps. So we're optimizing the number of pumps. You can see instead of having 4 pumps on half the day, pretty much half the day, or even more than that, you only need 3 pumps on out of 4. And during the peak demand, we'll use all 4 pumps in the first pump station. In the second pump station, even the difference is more. So only pretty much 2 pumps, and then we keep adding until we hit the peak hour demand throughout the day, which would require more number of pumps being active. So that's one difference that we made. The next mode of pumping in here is, again, all pumps on, just like the first scenario that we're not showing, but we're optimizing the variable speed setting on each and every single pump. 4 pumps in pump station number 1 and 6 pumps in pump station 2. You can see outside peak demand hours, pump speeds, PS, the dotted line, is going down, and as we go throughout the middle of the day, we're going to have more higher speeds. Same thing for pump station 2. So that was the second scenario for optimal pump scheduling. Now, the third scenario is we are going to use active pump index. So we find the number of active pumps, but for those that are active, we're going to use variable speed for all the pumps that are on. So we can see that the number of pumps are just like this mode of pumping, similar, but the speed is also not constant, just like this mode. This pumping speeds are going up and down and adjusting, and they're being optimized based on the pumping regime or the diurnal demand that is changing throughout the day. And the last, and perhaps in my opinion the best, that those software packages in industry would not be able to beat is combination of variable speed pumping, fixed speed pumping, and active pumping index. Again, I encourage you to go and find the paper and look at how we can build up from left to the right, and we can more and more optimize the operation of the pumping, the pumping station. So in this last one, what we do is we try to also minimize the number of concurrent variable speed drives. So that's the whole point. In the previous one that I'm hovering the cursor around, we have multiple variable speed drives. That is, if we have 2 variable speed pumps that are pumping has half the speed, why don't we turn off one of them and maximize the speed of the other? So on the right hand side, we're trying to go into that direction and minimize the number of variable speed drives, because variable speed drives, when you turn down the pumping speed, the efficiency of the pump will be questioned, and it's not, in terms of energy, if you have 2 half pumps, they would use quite a bit of energy. So that's the gist of the last pumping scenario. And now if we want to compare all of these five pumping modes or philosophies in terms of net pressure reliability index, which is like the pressure across the system for all of those junctions in the system, leakage around the whole system, and how they change throughout the day. These are extended period analyses for 24 hours, and also power consumption. You can see that in each case I've highlighted the best solutions. Not always the last one is the best, but it is usually, when you look at the last row, it is one of the best solutions that you can see in terms of improving net pressure reliability index, which is the performance of the system from the consumer's point of view. Leakage, that is like water loss, because of the pressure management, you're turning off more pumps and you're saving excessive pressure that drives leakage throughout the leaky parts, cracks and fissures that we obviously have throughout the whole system. And also power improvement in the pump station itself. So these are 3 different things that we would want to consider when operating the water distribution system. when it comes to pumping regimes. So in terms of net pressure reliability index, you can see the best solution is achieved simply by using our the method API and active pump index, hands down. So you need to optimize the number of pumps before doing anything to achieve the best pressure performance. And you can see API is improving compared to FSP, fixed speed pumping, with all the pumps on, active pumps 10. And here active pump index is 6.7, meaning that you need somewhere between 6 and 7 pumps out of 10 pumps in the system. You're achieving the best kind of pressure improvement in the system. So that's exciting, that's interesting. And the second best is FSP VSP API. We have a combination of optimize the number of pumps and minimize the number of VSPs and optimize the pumping adjustment, or like pumping speed for variable speed pumps. It's going to be one of the best solutions in here. Moving on to the leakage, again, you can see fixed speed pumping with active pump index optimized. That is the best solution. The second row, this is the best improvement, leakage improvement, compared to the baseline with FSP all the pumps on. And the second best is FSP VSP API, which was in the previous slide the solution to the right hand side, and is highlighted and it's shown in blue dotted lines, dashed lines. And in terms of power or energy consumption in the pump station, the best one in red dashed, you can see it's FSP API, which is the number of pumps that we're optimizing. They're all fixed speed pumps. And then the second best is FSP VSP API, which is fixed speed, variable speed, and active pump index optimization, pretty close to each other. And you can find a trace of, in any of the indicators you want to improve, be it pressure, leakage, or power, there is a trace of API usually. Either this one, or this one, or this one, the one on the end. There's a trace of API being one of the best solutions. Something that's absolutely ignored in WaterGEMS or InfoWater. So that was quite an interesting point that we came up with. So just to wrap it up and to conclude, optimization is becoming an important part of industry work. If you're trying to find some sort of position in consulting and in hydraulic modeling and simulation, if you're interested, it's just not working with the optimization software, but it's also optimizing hydraulic modeling software. It's about optimizing the solutions. And if we're going to get another chance, I will publish another video for you guys about application of optimization in calibration of sanitary systems, as opposed to optimal scheduling in water distribution systems. It is becoming more and more mainstream, and you want to go beyond modeling, which is just running the model, looking at the results. You want to automate and optimize the solutions so that you can look at the variety of different solutions that you could achieve using your hydraulic modeling results and find the best or optimized solution. So going back to pump scheduling specifically, we optimize not only the pumping status, but also the number of active pumps, just to reduce the number of possible solutions and to get focused on the best solutions that we can find in billions of different possible solutions. And we not only looked at the computational possibility by optimizing the number of active pumps, meaning that we could reduce the number of active pumps and have fewer possible solutions that we could compute, and that would basically make it more feasible to find the real optimal solution. So that was considered as the main point. And also, usually, as we used to do, we would look at pressure and leakage or electricity, which are all highly correlated. Once you save pressure, you're going to save leakage and you're going to save energy overall in the system. It is also about the ease of operation, because we wanted to minimize the number of concurrent variable speed pumps, which is what you get from WaterGEMS and InfoWater anyhow, which is not very operational. It's not something that the water distribution operator would like to see. So that's another thing that we looked at and we achieved through this real case study, or one real case study and one sample system. So I would like you to stay in touch if you got any questions, because this is a video and we don't have the chance to interact with each other and discuss any questions that would arise. Here's my LinkedIn. You can find me and you can send me your messages and your questions. And thank you very, very much for your interest in this topic. I hope that the slides have been informative for you. And thanks again for your time today.